Okay, so it's 1:45. Let's get started on this next session. We're going to be talking about IBM's next generation power processor roadmap, as well as its memory roadmap. My name is Brian Allison, and along with Madeline Vega, we're going to do kind of like a co-presentation. My background is I'm a logic designer based out of the IBM Rochester development site in Minnesota. I've been doing power or doing chip generation or chip development for about 25 years now. Most specifically, I've been working on CAPI and OpenCAPI over the last 5 or 6 years. So I've been spending a significant amount of my time working with partners and doing acceleration development, whether it be OpenCAPI, NVLink, those kind of constructs.
Hi, my name is Madeline Vega. I'm the chief engineer for the next generation of power systems. I've also been working the last couple of years on the new emerging memories that we want to get into power, and then we'll talk about the OMI and OpenCAPI and connecting memory through that.
So I always like to kind of get a little feel for my audience here. So how many of you folks are like in this scale-out type of environment? How many are in the scale-up environment? How many are in the cognitive environment? How many are new to power? Okay, so I'm seeing a smattering of hands all over the place. Okay, so the focus of today's talk is to really talk about the next generation of the power processor. We call it AIO, which is advanced I/O. Today, we've got two types of machines that are out there. We've got a scale-out environment as well as a scale-up environment. Scale-up is kind of like the enterprise-type clusters. So if you're doing IBM I or AIX, where you're doing 4-socket and larger, that's a scale-up environment. On the scale-out environment, right, that's where you're going to get into your Linux-type environments. I also consider a lot of the AI cognitive systems like the AC922 as part of the scale-out environment as well. What you're going to see here is there's going to be a fundamental shift in my mind in strategy of where IBM is going as far as what our systems look like. Out in the industry today, it's kind of my opinion, cores are becoming more of a commodity. It's very much very difficult to differentiate yourself just going core to core. Now, obviously, you've got to have a strong core, you've got to have strong threads, but based on a lot of these emerging workloads, you've got to be able to support heterogeneity, right? And accelerators are becoming more and more prevalent, right? So the overarching theme, I think, from all the talks that you've heard from this morning, right, there's a lot of open initiatives based on acceleration, right? And so we're obviously doing chip and system development, right, around these accelerators. Today, in the scale-out environment, it's very traditional. You've got direct memory attach, right? That's one approach to building out your, let's call it your memory infrastructure. And then on our scale-up type environments, right, we've got buffered memory. Now, Madeline's going to talk a little bit about what we're doing with our memory subsystems that we're doing in the advanced I/O area. But what you're going to see is there's a lot of different emerging storage class memories that are going to become more and more prevalent as we go over time. And you actually have to be able to address those environments. Now, you can't really do those types of things just doing direct DDR memory, right? You have to have an environment where you're able to scale, right, to actually have a large memory footprint, have a large bandwidth type environment, and then to address these emerging, storage class memories. So what you're going to see today is, on the scale-out environment, we've got 8 direct connect DDR ports. We can get up to 150 gigabytes per second of sustained memory bandwidth. We've got PCIe Gen 4. There's 48 lanes of it. We're the first ones in the industry to basically have that adoption for Gen 4. Others are following, suit over time. We've got advanced I/O. We've got 25 gigabit signaling for OpenCAPI as well as NVLink. So there's some differentiation that we're doing with acceleration with the NVIDIA GPUs, as well as what we can do for OpenCAPI. And then you'll see that with both our scale-out and our scale-up type environments today. Now, as we're moving forward into the 2020 type time frame. We're still going to be on a 14 nanometer node from Global Foundries. We've got a whole new memory subsystem that Madeline's going to talk about. We still have PCI Express Gen 4. We're still going to run all of our NVLink and our OpenCAPI accelerators at 25 gigabit. But then we're going to go to OpenCAPI 4.0. So you heard some of the discussions this morning about some of the initiatives that we're doing where we're opening up some of our reference designs around OpenCAPI 3.0. But we're going to open up those environments today, but then we're going to migrate to OpenCAPI 4.0 when we get into the P9 advanced I/O chip development. And then in 2021, we're going to have our Power 10 processor. I think most people are aware that we're using a different foundry partner for Power 10. We're going to go to Samsung 7 nanometer. Along with that, you're going to have a new microarchitecture. You're going to have additional memory bandwidth. We're going to go along with PCI Express Gen 5. And then for our advanced signaling rates, we're going to start to go to 32 and 50 gigabit. So what you'll see along with that, you'll see the next generation NVIDIA GPUs, and then you'll see those next generation GPUs also with the system that we're coming out in 2020. So there's a new revision in 2020 of NVIDIA GPUs, and then there's another one in 2021. Any questions so far? So Power 9. So I just wanted to kind of reemphasize, this is one of the premier acceleration platforms that are out there. We've got a number of different interconnects that are meant to address acceleration technologies, whether it's PCI Express, whether it's the 25 gig common link, which by the way is the same PHY signaling that we use for NVLink as we do for OpenCAPI. We've got some on-chip acceleration as far as gzip engines, compression engines, some SHAWs. Those are available today as far as upstreaming the code. We've actually got a relationship with a synchrotron over in Europe where we've been doing some metrics of looking at our on-chip acceleration. We're seeing some really compelling results with that. It's my expectation that those engines will be available sometime later this year for other partners to take advantage of, but we're seeing some really impressive results. We've got the second generation of CAPI 2.0, which is basically our second revision of when we did acceleration on PCI Express. We've got NVLink, like I talked about. We've got OpenCAPI 3.0 as well, and then OMI, which is our open memory interface, which Madeline will talk about. Now, most people are aware of this, right? The systems that we built today with the AC922, they're powering the two largest and most powerful supercomputers in the world, right? In Summit and Sierra at Los Alamos and Oak Ridge, right? It's all powered by, Mellanox, NICs, and NVIDIA GPUs, right? That's something that we stand behind and that we're very proud of. Now, this is kind of an eye chart, but I'll kind of go over some of the main differentiators and things to pay attention to. So this is what we call our advanced I/O chip, right, which is going to be our next generation platform. Sometimes you'll hear it called Swift. It's basically our AC922 follow-on for the cognitive space. It's got, again, 24 SMT cores. It's got 120 meg of L3 cache. It's got still the same 25 gigabit low energy differential signaling for everything that we do, for OMI, for OpenCAPI, for NVLink. It has the capabilities to go from 4 socket to 16 socket as far as being able to address the enterprise space. It's got PCI Express Gen 4, still have 48 lanes of that. So what you're going to see is that there's just an abundance of interconnect for acceleration, interconnect. Now, one of the other things that we've addressed, like I said, is OpenCAPI 4.0, and I've got a slide later in the deck to talk about what some of the features are with 4.0. But what you're going to see is that this guy is very much meant to address all these acceleration technologies. Now, one of the things that we kind of point to on the bottom is these technologies don't do a lot of good unless you have a superhighway of on-chip bandwidth. So there's 2 terabytes of raw signaling bandwidth shared by all these different attach mechanisms to basically handle all of the incoming and outgoing traffic for NVLink, for OpenCAPI, for OMI, things of that nature. So this chart is really meant to just kind of show you, it's a pictorial diagram of what you could build as far as what we're looking at for this advanced I/O, right? We've got OpenCAPI interconnect, we've got PCI Express Gen 4, we've got OMI memory, which Madeline, like I said, is going to talk about, and then the ability to have, let's say, 24 lanes of NVIDIA GPU interconnect, running at 25 gigabit. So you're going to have just, a ton of bandwidth, going back and forth between the processor and then the NVIDIA GPUs, and then, a balanced memory construct as well, because that's also running at a 25.6 gigatransfer signaling rate as well. So let's talk a little bit about our OpenCAPI design goals. One of the things that was talked about this morning was opening up some of our reference designs for the open memory interface, right, for the host side as well as the endpoint side, as well as doing an endpoint OpenCAPI reference design for the device side. So, you've seen a lot of, let's call it industry buzz around CXL from Intel. OpenCAPI has been out there for, a couple of years now. We have all of those similar constructs and even more. So today we have the ability to address coherent caching accelerators, to support network controllers, to support differentiated memories, whether it be ReRAM, MRAM, what have you. It's able to sustain very high bandwidth, very low latency. So it can handle all these different constructs of all these new emerging storage class things. We also can look at things like storage controllers. Now the design today is an asymmetric design, which is pretty predominant in the industry. That's what CXL is doing, and that's what others are doing as well. It embodies the ISA of the host architecture. We want to make sure that the accelerator development is very easy for those guys in that type of environment. So we need to hide the differences between the coherence and memory models, address translations, and all those types of things. We want to put all the complexity in the host and not in the accelerator. And that's what you're going to see as part of this environment. Now, it obviously takes many years to design a host CPU, let's say 3 or 4 years. We want to keep it on, a very shorter development cycle for folks that are doing accelerator development, typically less than a year. And so we're trying to build an ecosystem that allows for folks to do accelerator development on OpenCAPI. And one of the things that there was an earlier presentation from Lu Yang from our China research lab where she talked about OCXL, which is a higher level programming framework for folks that want to do FPGA development. Those are one of the things that we're trying to do to address that type of environment. The other thing that we're trying to do is that the timing corners. Obviously, in an ASIC and an FPGA, you're not going to want to run at 2 gigahertz. You're going to want to run at 400 megahertz or slower, right? So we want to run at these lower frequencies. So when you're doing your timing optimization, it's much easier to do it at those types of frequencies than trying to do something at a gigahertz or greater. So we're basically making that a lower barrier to entry. Trust is another thing that's very important as far as all the accelerators go. One of the things that we do is we make sure that all the translation gets done in the host. Everything is a virtual address space. So there's never a physical address running around that somebody can basically tap on the wire and do some nefarious types of things. So we basically are building trust into the architecture itself where everything is running in the virtual address domain. And then obviously cache coherence. We want to make sure that all of our accelerators, whether it be an NVLink or an OpenCAPI or what have you, can participate in our caching structure, whether it be in the L2 or L3 or what have you. We want to make sure that it participates in our cache coherence. And so we can't count on the accelerator to do that, so we make sure all that gets done in the host. So one of my last slides, this is kind of just IBM's history of roadmaps around acceleration, right? We started this game around 2014 in Power 8 with CAPI 1.0, right? It was very limited in the sense that we only supported a single cache line in 128 bytes. It was tunneled over PCI Express Gen 3, and we didn't, support a lot of things like native DMA or atomics or, host memory, attach agents and things like that. So it was pretty rudimentary at that point in time. It's taken us relatively around 4 or 5 years to really get it right? With CAPI 2.0 and CAPI 3.0, we're able to basically sustain bandwidths on OpenCAPI 3.0 around 22 gigabytes per second, right, out of a 25 gigabyte possibility. And even on CAPI 2.0, where you've got PCI Express Gen 4, where it's 16 gigabit, we're able to get a little bit north of, like, let's say 13 gigabytes sustained when we run that accelerator. We've got all these additional features and functions that we've been enabling over time. The ability to do native DMAs to host memory, to do atomics from the accelerator to host memory, the ability to wake up a host thread instead of doing interrupts as your handoff mechanisms, and then the ability to do, like, let's say, memory attach off of an endpoint device. So if you've got some sort of storage class memory, you want to run it off of your accelerator, whether it be just traditional DDR or whether it's ReRAM or something like that, you can start to do hybrid memory solutions once you start to get into OpenCAPI 3.0 and beyond. Now what you're going to see is, you know, with OpenCAPI 4.0, a couple of the different capabilities that are in that, that Power 9 Advanced I.O. chip is we support the ability to do posted operations, just like PCI Express does. And then we're also able to do like low latency short messages from the host to the accelerator. Historically speaking, it's all been MMIOs, whether it's 4 byte or 8 byte. We're actually going to be able to push messages of the 128 byte variety down to the accelerator. There's a lot of applications and solutions that kind of demand that. And then the ability to actually have an accelerator cache underneath the processor's caches, right? That's all now capable in OpenCAPI 4.0 in that new chip that's coming up. Now with OpenCAPI 5.0, which is coming in our Power 10 processor family, right? That's coming out in a 2021 kind of time frame. This is where we get into some of these more, let's call it advanced interconnects as far as being able to run at 32 gigabit or 50 gigabit. Like I mentioned earlier, that's going to have a new NVIDIA GPU associated with that. And then it's going to be able to do, let's call it interoperability. What we're trying to do is, with OpenCAPI 5.0, we're trying to make it such that somebody that develops an accelerator on PCI Express Gen 5 can interop with the host processor's OpenCAPI. So you actually don't have to have a separate PHY for OpenCAPI 5.0 relative to what we did historically speaking. And I'll just leave it at that, and Madeline will take over from here.
Thank you, Brian. Hey, everybody. So even yesterday when we had the keynotes from Steve Fields talk about what we're doing for our systems, our memory strategy is changing. In the Power 9 family, we have the Power 9 with the scale up, with the scale out. In the scale up, we use the buffered memory. And then in the scale out, we have the direct attach. On our next revision of the Power 9 system with the Power 9 Advanced I.O., we're moving that to what we're calling the OpenCAPI memory interface. And it's going to have all these qualities that Brian mentioned before. And we're moving that way because we need to have, for the next generation of memories, we will need to have extreme bandwidth. We're looking for something that is going to be common and that we can use to connect different type of memory technologies. We'll talk about a little bit about storage class memories, but that's something that is new and emerging, and we want to be ready in our processor to support any of these types of technologies in the most efficient way. We will also make this a common design that we will keep the RAS features that we currently have on our enterprise systems. We will also make sure that we can have a lot of capacity and bandwidth on it. And it will also support as I mentioned, different technologies for memory, including storage class memories. This is how we're moving from, in our systems, we have what we call IBM Center Dims. It has a buffer that has an L4 cache. It has extra RAS. And this one, however, is only used in our systems. And then we had on the scale out, we had the JEDEC standardized industry standard DIMMs. And as we move forward, we're going to the technology agnostic. We're changing the form factor, but we're going through JEDEC to standardize it. It will be low cost. It will have the enterprise reliability that is needed. The latency, even though we're putting a buffer in, there's a lot of innovation, and there's a buffer that Microchip, they will talk about later in another session. They've done a lot of innovation to make sure that the latency doesn't go much higher than the direct attach memory. And because we are connecting through the high-speed serial buses at 25.6 gig, this is going to have a lot of high bandwidth with all the ports that we have. On our processor, the P9 AIO, we're going to have 16 of these ports, 16 of these by 8 ports at 25 gig. So why are we continue? Our message is that OMI is the right thing to go for memory. And it's because it's going to be low latency, high bandwidth, and it's going to be technology agnostic. We don't have to wait on another processor development to introduce new memory technologies. We don't have to have a specific memory controller inside the chip. We put that in a buffer on the DIMM, and then we can support any of the transitions, like when we go from DDR4 to DDR5, whenever it makes sense, whenever the cost goes better for DDR5, we'll already have systems that are ready for it. It will also allow for the new technologies and emerging memories, just like stacked DRAM, low latency DRAM, things like that. And it was mentioned on a previous session, for the technologies of the future, we need to be able to do that extra bandwidth, and with having all these parallelized and all these pins, the processor, you will be using a lot of real estate to be able to put all these into the processor. With OMI, we're serializing that, and that way we get, we're able to allow for, I'm sorry. So we're able to save those pins from the processor to get them to a better use of your silicon. And the big point is through standardized through the OpenCAPI, which we have, it's open. We're standardizing all these DIMMs, differential DIMMs. We're standardizing them through JEDEC. And other CPU architectures can use OMI and OpenCAPI. This is not something only for power. And of course, we want to make sure that we establish this as a technology that other manufacturers will use to lower the cost for it. As mentioned, the signaling rate is 25.6 versus a DDR at 3200 megahertz. So just raw bandwidth, we get a 4 times improvement. We are only having between 5 to 10 nanoseconds that we're adding into the latency. So we want to make sure this performs just as any other industry standard memory. And the microchip SMC is going to be that first buffer that we will use on our systems. We worked with them to develop it, but it is their design, and it can be acquired through working with them. There's different chip vendor, DIMM vendors that are working with them to build these new DDIMMs. So here's, from a processor perspective, we have our high-speed signaling transmit. It goes through the DIMM. They do the different functions like lane DSQ, fast activate, and then it gets to the DRAM and back. And we're making it, this microchip SMC 1000, it has the innovation to keep that latency to the minimum. We don't want to affect performance, but we want to keep all the other benefits of OMI. And the good thing also is, like, once they've done this type of buffer, we can reuse that type of that side, and then the other, media controller, controlling the media is something that you can add into different type of buffers to support other technologies. And as I mentioned before, this is the way we're going. For Power 9 Advanced I/O, we have the CPU, we have OpenCAPI, which we also have in P9, and we have our OMI slots. We will be able to put different memory technologies in both type of interfaces. The ones that go through the OMI, it's something that is more optimized for memory. And then the ones that go into OpenCAPI, it is a bus that is also used for accelerators. It will have a little bit of extra latency, but we believe some of the technologies that we put out there will still be very useful and performance and cost efficient for some workloads, and I'll talk about that in the coming slides. Another point I wanted to make here is that even for P9, which is what it's out there today in the market, we're going to be able to put some hybrid memory subsystem, like memory that is combined with storage, back to making it low cost for specific applications that can get the work done with a little bit of extra performance degradation. So we will be able to, on P9, existing P9, we'll be able to use this hybrid memory subsystem on the OpenCAPI ports. As we move to P9 Prime, which is the P9 IIO, and P10, we will be able to also put all these memories into the OMI channels. Another thing that Brian mentioned once, a few times is like storage class memory. So what is that? It's all these new emerging technologies that have properties like memory and properties like storage. The main thing is it's byte addressable like memory. It is fast, not as fast as real memory, but it's much faster than storage. And also, the key is that it's persistent. So as we have many workloads now, like in-memory databases, you want to be able to have your data there and not have to go all the way to your disk to get it back if the database has to be restarted. So the persistence qualities of storage class memory are great for the use case of quick restart of in-memory databases. And we see that as one of the use cases. We are going to show you that hybrid memory subsystem to address these. Another key that we see is not just about quick restart of applications that have your data in memory, it's also about cost performance. If we look at the whole spectrum of technologies, you have your DRAM, it's volatile, it's very fast. It's the best that you can get for performance. And then you got your NAND that is used today for storage. It is persistent, but then that's very high latency, and it's not fast enough for just to be memory. But it is persistent, and it's very, very low cost. There's new technologies out there today that are called LLNAND, low latency NAND, and it gets a big improvement in the latency that it has. Instead of hundreds, thousands of microseconds, you get it less than 10 microseconds when you're in the low latency NAND area. So you have all this range, and we need a way of how do we use all that range as memory to be able to tie it to the best cost performance in your applications. So with that, we have been working on this hybrid memory subsystem. Our design here is, and this will be available with P9 systems. And it will be through the OpenCAPI slots. The main thing is, let's use this low latency NAND technology that is available today. It is still too slow to be just used as memory. But with OpenCAPI, we do have a mode that supports memory semantics, load store memory semantics. So we will put big capacity of low latency NAND in that card, and we will have enough of the DRAM as cache. We have an FPGA. We're working on the memory controller right now is an FPGA, and we're doing all the media, everything that you have to do for the media, because it's still flash, so it doesn't have the endurance as DRAM, so it does a lot of media management. But we will also have there the controller to be able to cache and prefetch enough of the data into your DRAM so the application doesn't see that it's very far away, your data. And the primary application we're going after is the in-memory databases. When you know that it's like for OLAP type of workloads, when you're doing analytics, and then you know where you're going, so if you know where you're going and what you need to get next, we're going to be able to hide the extra latency of the low latency NAND. And this card, we've been working on it as a partnership to get the media, but also for my adapter development and design, Bitware has built the card here. It has it is a form factor of PCI, so it would go into your existing systems. It has a form factor kind of like M2 sticks. It's not M2 protocol that we use, but from a physical perspective, it just looks like an M2. Then we have 4 of them here. Those are the ones that have the low latency NAND components. Then that is connected to your FPGA, and through the connectors of OpenCAPI, you get your power from your PCI slots on the system, but then you get your data talks through OpenCAPI. We're working right now, this is prototype that we have. We're working in the lab with them, making sure everything works, and also get everything worked in the memory controller to get the performance that we need for these. And what we believe is that these will have a cost point that will be attractive for those workloads. And we also believe that in the future, it's going to be a lot of different tiers of cost performance. Depending on your application, you might want to use these. Depending on other applications, instead, we will go through OMI, either to DRAM with the microchip buffer, or we will go to something in between. It just depends the right point for the workload. When is it okay to go slower to slower media? When do you really need to be fast? And with OMI, it will be very flexible because we can connect anything to our Power 9 advanced I/O and to our Power 10 processors. If you have questions about it, so we have the card. It's in the Bitware booth. And then just to summarize, the talk today was about our roadmap with Power 9. The final addition that we're having in the family is at Power 9 AIO. And as Brian mentioned, it's not a lot. We're not making any changes in the core of the processor, but everything around it. The I/O is where we're putting all the innovation in this one, because it's all about, we might not get all the differentiation in core strength right now, and in the future, the next technologies will get that. But for right now, we're making sure that also all the bandwidth that you get works well from the different, just not to get into the memory, get into your I/O, getting the data where you need it to get the best performance possible. Is there questions? Yes.
If I don't actually need much memory bandwidth, and I have just a standard workstation, will I be able to use new Power 9 CPU with standard Dims?
So you will, now that we're moving into the OMI, you will still need to have a buffer or some controller in between. So we will get from the Power 9, from the processor, you will have your OMI interface for memory, the OMI. But you will need something to talk to your DIMMs, and it could be industry standard DIMMs, so you have to put that into the planar. That is a supported configuration.
Maybe it's too early to talk about prices. You mentioned maybe price effect.
Yeah, so the systems will go out next year, so there's right now work with the different vendors on what it is. And the main thing is on the buffer, we wanted to make sure that it's going to be competitive pricing. I cannot say, tell exactly what it will be. Yeah. Yes.
You're using VNAND or the Toshiba SL?
ZNAND. Yes. See. He was asking which type of low latency NAND we're using. Okay. Any questions for me or for Brian? Okay, we appreciate it. Thanks for coming to the session.